Welcome to the course on power electronics with wide bandgap devices. Today I am going to discuss about the power density considering the wide bandgap devices. I need to tell you what is the power density. So what generally we consider when we say power density, because like in the entire course sometime probably I have mentioned that whenever we consider this wide bandgap devices, the power density of the system it will be higher, and that is desirable for any power electronic system. So that is why people are going towards this wide bandgap devices so that they can go for high power density system. So let's see what is power density. So definition of power density. So definition of the power density, when I say, so that time, so the power, how much power is processed in given space. So that is known as the power density. If power process, that measurement is less in a given space, then we can say low power density, and if it is more in a given space, then we can say high power density system. So basically the definition for this is that power can be processed in a given space. So generally what happens for silicon devices, like considering low frequency operation, we need the component which is having higher value. Component means the inductor, capacitor, and heat sink for the silicon based system. So then the same space, like if we consider for silicon, so like amount of power it will be processed for silicon based system. So power P1, let's say it is processed in this particular space. And for this wide bandgap devices, this can be processed in the same space 10 times P1. This is just an example. So then what will happen? If in silicon P1 power is processed and in wide bandgap devices it is 10 times P1 is processed in that space, then we can say this is high power density system, and that is what is desirable. Right. Now unit of this is that watt per meter cube. Watt per meter cube. So meter cube tells like the space where 1 watt power is processed. This can be also expressed in terms of watt per inch cube or watt per centimeter cube. So whatever inch, meter or centimeter, that gives dimension of the particular space, and watt is obviously the unit of the power. So like if it is like high power density system, so maybe it can go towards kilowatt in that kind of level. Okay, so this is known as the power density, and as you know, like now everything is going towards like compact kind of system. The size of the system is reducing, so then power electronics converter size should also reduce. So then if we want to reduce the size, we have to process high power in a smaller space, right? So then we have to go for high power density system. So as we are going to use wide bandgap devices in future power electronic system, then this can be easily achieved using wide bandgap devices. But there are problems or challenges which we need to face if we go for high power density system. Okay, so then what limits the power density? First we have to know that, see, in silicon also we can go for high power density system, but there must be some limitation of silicon based devices which doesn't allow us to go for high power density system. Now for wide bandgap devices with this limitation can be solved. Let's see what are these limits. Limits of right. So what limits the power density? Okay. So basically there are different limiting factor of this power density operation. So one is that power losses. So this power losses in the power converter which happens, this comes in the way of achieving high power density system. Now what are these losses? So these losses can be classified conduction, charge related losses, reverse recovery losses, turn on and turn off losses. Okay. Right. So these are the different losses which causes this power density problem. Okay. Now what are the other problems? So this losses will generate heat in the system. In order to reduce that heat, we need to use heat sink, or we have to use method, or maybe like we can increase the size of the system so that like the surface of the surface of that particular system will be much wider so that it can dissipate heat easily. So the heat generation in the system will be less, and you know the problem of thermal related issues. So if heat generation is more, obviously the property of the devices will change, and again it will generate more heat, and eventually system breakdown will happen. So that is why we have to manage this losses, generated heat properly, so that it will not affect the system. And then second thing is the thermal management. This is also related to the losses. So basically we have to manage all the heat generated in the system by using proper method, and that causes increase in the size of the system. Okay, so in order to reduce the problem, probably the first thing we should be considering is the reduction in all the losses, or probably better thermal management of the system, or combination of both. Okay. Now how to break through this problem? So how to solve this problem? As you know, like switching loss we can probably reduce. Reduction. Second is that improving package thermal performance, modern circuit technologies using wide bandgap devices. This all this I'll discuss in details. And then go towards integrated kind of solution, integrated circuit solution. Okay, so these are the problems and this is how we can solve. So let's see how this power density is trending. Starting from the beginning means when this semiconductor devices first came and then power electronic system developed due to that. From that time to now, where we are exactly in the power density point of view. So if you see power density trend means how basically this system size changed, right? So system size, if I write down, so starting from 1, so the scale will be like different scale you can just consider. Log scale you can consider 1000, then it is 10,000. So this is millimeter cube per ampere. Okay, so this is the magnitude in this y-axis and the x-axis gives the year starting from 1990, then 1995, 2000, then 2005, 2010, 2015, 2020. Right now we are in 2025. Now it is 24 is ending, so we are in 2025 and then it will go further 2030, right? So now this curve looks like, so basically it is going from 10,000. So if I draw a dotted line, so then it will look like something like this. Okay, so now in this, so if we, so just let me draw it. Okay, so now we're starting from 1990. So there are like different generation semiconductor devices like we started using from 1990 right now 2025. So then we can write down the semiconductor devices with respect to generation 1, generation 2, generation 3, generation 4, generation 5. Okay, now let me just use different color. So here this line is with respect to generation 1. Now this is the first semiconductor device when started using. Then modified device when it arised, so then what happens? So then we are in generation 2, right? Now after that there is like here around generation 3, now generation 4, and then we are going towards generation 5 here. Okay, so this is how this power density trend is. Now recently we are using generation 5 semiconductor device, and that allow us to have very small size, 1 millimeter cube per ampere. Earlier it was close to 10,000 millimeter cube per ampere. So that much space is used for that much current process. Okay, so 1 ampere current is processed in 10,000 millimeters cube space, and now here it is 1 ampere current in 1 millimeter cube space. So this is how this power density trend is evolving. Okay, now probably in future it will be further less, so that is that prediction only we have. Until and unless there is like proof, we cannot comment on it, but trend is going towards it. Okay, now this, let's see how we can actually analyze these different power density limits. Okay, so if we have to consider power density improvement solution, if we have to provide, so then how that can be provided. So let's see that power density So first thing, so there are point wise, let's see how it can be done. Point 1 is that increase the switching frequency. Okay, so this is the first step can be taken. So if we increase the switching frequency, then what will happen? Passive component size will reduce down. So passive component, among passive component, which one is directly related to the frequency? That is magnetics or the inductor. If the system is isolated, if there is a transformer, so then it will consider the transformer. So then inductor, how it is related? L equals to duty cycle of that particular converter multiplied by voltage across the inductor divided by switching frequency multiplied by the current ripple of the inductor. So this is the basic formula which you can refer in any power electronics book. You can get it very easily. So basically V L equals to L di by dt. So from there this can be derived. So now you can see here, so this L, it is basically inversely proportional to the switching frequency. So if switching frequency increases, then the L size will reduce down. If L reduces, then what will happen? The requirement of magnetic size will reduce down, and that will increase the power density of the system. Okay, this is one of the ways. Now second thing what we can do, second thing we can consider is the reduce by reducing switching losses. So the switching losses, if we can reduce down, then what will happen? Heat generation will be less. If heat generation is less, then the heat sink requirement will reduce down, and if heat sink requirement is less, then it will improve the power density of the system. So now there are different losses, you know, that turn on and turn off losses, conduction losses, charge related losses. All these different parameters are there. If there is a possibility to reduce down, that we can do. One of the ways is that the amount of charge in semiconductor device is related to the on-state resistance. Now somehow if we can reduce this on-state resistance, then that can be reduced down. So a lower resistance results in higher gate charge. Right, and possible capacitances or possible conduction loss can be reduced. Loss reduces okay, and then switching losses can also be reduced down, but there is a problem. So basically loss due to conduction can be reduced down, but in this case switching loss cannot be okay. So in the previous, basically if it is possible to reduce the on-state resistance, then what will happen? Then the loss in the switches due to conduction can be reduced down. Now switching loss, if we consider like higher gate charge, then the switching loss cannot be reduced down. So if resistance reduces, then conduction loss will reduce, but the charge related loss will increase. And charge related loss, if it is increasing, then the switching loss will increase. Then reduction in the switching loss is not possible, but conduction loss in the switch is possible in this way. So then what we have to do? We have to consider reduction in charge related losses. So what do you understand by charge related loss? So charge, when I am saying, so basically it is related to some capacitance. So how this charge related loss comes? So basically drain charge, if I write down charge in charge related losses, so then that can be write down as half CDS CDS is the drain to source capacitance, and then this CDS multiplied by VDS square. So whatever voltage is appearing across drain to source in the devices. So this is with respect to the MOSFET. In IGBT, it will be like with respect to collector to emitter. Okay, so collector to emitter the capacitance, and then with respect to the voltage across it, and then that multiplied by the switching frequency. So this CDS, if it is increasing, then the charge related loss will increase. So this is with respect to the drain charge. So there are actually two different charge related losses. One is with respect to drain charge, another with respect to gate charge. For MOSFET, so that is equal to QG, VG and FSW. VG is the voltage which is coming across the gate to source, and QG is the charge required for that gate to source. Basically the capacitance which is connected at the input of the device, which is known as the gate capacitance. Okay, in order to reduce the losses, we have to consider this parameter which is less in the devices. So then what we need to do to reduce these losses, this charge related basically losses, drain charge and gate charge related losses, primarily this QG primarily the switching frequency need to reduce down. Now if we reduce this switching frequency, then that will increase the passive component size. So this is not desirable. So there are actually two components, input voltage, output voltage and the gate voltage, they are fixed. So other things are the gate charges or CDS and the switching frequency. Switching frequency we can reduce down, but that is not possible for high power density system because we are going for high frequency operation. Now then remains QG and CDS need to be selected from MOSFET datasheet. Which will be of lower value. Okay, so this we need to check. That will help us in improving charge related problem or loss problem. Okay, now there are actually two things. Either we can reduce the conduction losses or we can reduce the switching losses. Both cannot be reduced at the same time. So then what we need to do? We have to optimize these values. Trading off means if we optimize, we have to see like which parameter is causing more losses. If charge related loss is more with respect to the on-state resistance loss, then probably we have to go for the this QG and CDS with lower value. If on-state resistance related loss is more, that is the conduction loss, then we have to consider lower resistance so that we can reduce the conduction losses. So that is why this trade-off between the switching loss and conduction loss we have to do so that we can select like which parameter we want to optimize, right? So accordingly we can reduce the losses, right? Fourth is the reverse recovery losses. the reverse recovery loss, how we can analyze? So basically this can be analyzed as the input voltage multiplied by the inductor current multiplied by the reverse recovery time of the diode, right, plus input voltage multiplied by reverse recovery charge of the capacitor. So these parameters tell us how much will be the reverse recovery loss in particular system, particular converter, if the diode is conducting. If the diode is not conducting, then we don't have to consider this reverse recovery loss. But most of the cases what happens, like forward and the reverse operation is there, so that is why the diode will come into picture even if there is no diode connected separately. But let's say boost converter or buck converter, they have diode connected separately, then we have to consider this reverse recovery loss also, how much it is going to be. Okay, there is no switching frequency parameter, so that is one thing we can see in this particular expression. So switching frequency will not come into picture in this, but like the reverse recovery time and the reverse recovery charge, that will come from the selection of the particular device, right? And device will be selected according to the switching frequency, so that I mean like all the parameters related to the device will not have effect in that switching frequency. So accordingly we can select the device, and from there we can check what will be the reverse recovery time and the reverse recovery charge, and then we can calculate the reverse recovery loss. Okay. Okay. So then this reduce the impact of diode reverse recovery through optimized design. Okay. Now this is with respect to reverse recovery losses. Another thing, important thing is that turn on and turn off loss. Although like it comes under switching losses, but this turn on and turn off which causes problem due to the presence of parasitic element, means parasitic loop inductance, this parasitic loop inductance will cause transient current to be present. So this DIDT problem and DVDT problem. So basically during turn on and turn off time, if there is like parasitic element, so there will be definitely parasitic element present in the system, and that will cause DIDT and DVDT. So basically current and voltage spike will be there, and due to this current and voltage spike, obviously then the system size will increase, because you know like if there is a spike in the system, so then we have to select the device as per the consideration of the spike rating. So based on that the device size and all the size of the components will increase, and that will causes increase in the system size and reduces power density. Okay, so then these losses need to be considered properly. So basically design has to be done properly so that this parasitic element can be reduced down, which causes the problem of DIDT and DVDT. Or DIDT or DVDT problem should be taken care of so that optimized system design will be possible. Okay. Now the thermal performance. So when I say thermal performance, so system heat dissipation I am talking about. So generally what happens, as I have discussed earlier, so heat generation in the system should be such that it will be able to dissipate through heat sink or the through PCB layout or through the devices. So it should be able to take off the heat which is generated in the system. So thermal performance of the system should be improved. So how that is possible? One of the ways is that, so required better packaging. Better packaging with respect to the device or any other component whatever will be placed in the system. So required better package for taking the heat out of the system. Okay, now this also requires the optimized package and PCB should be able to reduce the temperature rise in the presence of power converter loss. Okay, so hence system level thermal design is becoming popular area of research. So the main component where people are focusing is smaller smaller package component with good thermal performance. So probably people can look for the material or the connection how it is done so that this can be taken care of. Generally the thermal performance is like kind of can be characterized as with respect to the thermal resistance. So you can see resistance, thermal resistance, if it is like junction to ambient thermal resistance of any system like device or anything, it is increasing. So it is increasing like this. So then die area is increasing in this direction. Let's say. So as the thermal resistance is more, so then what will happen? Die area it is basically less. So it is like this. It can be sorry, you can actually, so it will not go to 0 because like then the system will not be practical. So it is having characteristics something like this. Okay, so you can see if the die area is less, the thermal resistance is actually more. So then heat generation of the system it will be more and then it will be difficult to dissipate. If the die area is more, so then the thermal resistance is less. so the heat generation in the system will be less and it will be easy to dissipate also. So this is how the thermal performance of the system can be characterized. So I mean both are complementary in nature, so we have to select the optimized design again. So everything we have to consider, like something we will be losing and something we will be gaining, so we have to choose the optimum point which will give us the required performance. Okay, so for anything this is like how it is done. So okay, just let me just tell you the final thing. So now these are the problems. So what are the problems I have just listed down? So basically power density improvement solution is that first is the switching frequency we can increase. So switching frequency we can increase, so that is that will again cause that will reduce the magnetics, but increasing switching frequency will cause some other problem anyway, like that will not go here. So we can increase the switching frequency to improve the power density, one thing. Reduce the conduction loss, reduce the switching loss, reduce the losses due to charge related losses, so that comes under switching losses. So basically reducing switching, conduction losses, all the losses, reverse recovery losses, and the parasitic element present in the system, and then improve the thermal performance of the system. So this will allow us to go towards high power density system. So now, so then if we go for this high power density system, so then what are the things we have to consider? So these are the things, these are the properties which we have to consider. Now what we have to do, we have to consider this reduction in the switching losses. How that will be possible? Let me just write down here. Switching losses, we are saying that we can reduce the switching losses. Then we have to consider here, this is possible by using switching loss innovation. So in this particular course we are discussing about wide bandgap devices, like how this switching losses changes in the wide bandgap devices. So if I consider, so this is the energy losses that if I consider, then what will happen if I'm not giving any values, I'm just comparing GaN with respect to silicon and silicon carbide. So this is how the losses are actually varying. So generally this is like with respect to GaN, the losses will be very small. For silicon it will be higher than the GaN, sorry, for silicon carbide, and this is silicon super junction. Devices. So you can see here, so loss in case of GaN device, it is much smaller than that of the silicon carbide, than that of the silicon superjunction devices. So switching loss innovation, if we have to consider for reducing switching losses, so then probably we can select the suitable device. We can go for the wide bandgap devices. We can use the GaN device in order to have very less switching losses. So this is where the innovation can come. Now next comes, so this switching losses, it will cover all the losses, means reverse recovery loss and charge related loss, conduction loss, everything. Okay. Now next is the thermal performance. When we say thermal performance, so basically I can just give you one example. We have to select like better packaging. So better packaging means, so better packaging, so we have to consider packaging part, packaging thermal innovation. How that can be done? One example I can give you, in the packaging innovation in devices, instead of using bond wear, some of the devices they are having bond wear, right? Instead of using that, we can go for this hot rod connection. So instead of this, this will have less thermal problem, or I can just give you better thermal innovation. So this is with respect to the device. Devices generally have bond wear. If instead of bond wear, if we can go for hot rod kind of technology, then it is having better thermal packaging. Okay. So this is hot rod interconnection. Okay. This comes under the device part. So we can actually select those kind of devices which have those connection which doesn't have bond wear, that will give us better thermal performance. Right. Now this all these thing along with advanced circuit topologies. So these all are the solutions. That is fine. We can choose different devices. We can reduce this package related problem by selecting proper packaging. Now, if we have advanced circuit technologies, which probably will help us increasing power density, that we can also choose. So all these things will give us the high power density system using wide bandgap devices. That is what is desirable for wide bandgap device applications. More about this I will be discussing in the next class. Thank you.